It would be pretty cool if we had an AI model that can go in and estimate the gaze, so in what direction are people looking just from a single image. Then we can combine multiple images in a video, so we just extract the frame from a video, throw it through an AI model, we do face detection, throw that information into a new model that estimates the gaze, in what direction the person is looking. Then we can do that for all the people in the frame and we can see where they're looking. So that's what we're going to do in this video here. Let's just jump straight into it. Inside the GitHub repository, we have this Gazelle framework or code base that we can go in and use for gaze estimation. So it basically just estimates where are people looking. I have another video where we went through it in a Google Colab notebook. Now we're going to write the code from scratch, basically see how we can set it up and do it on video streams. So here we can take a look at the architecture. First of all, it does scene encoding with a backbone, so just extract the features about the scene. Then we take our head prompting. We need our heads for our estimation. We have a gaze decoder, which is going to predict a heat map. So the heat map is just going to determine where's this person looking. Then we can apply that for all the faces that we're detecting. So we have a face detection model. You can use whatever you want. You can use YOLO, RetinaNet, or whatever. We take those face bounding boxes, feed it into our gaze model here. We'll get the heat map out, and then we can go in and draw lines, arrows, and whatever we want to use for visualizing in what direction the person is looking. You can see all the commands in here in the GitHub repo, how to use it and more information, but let's just jump straight into Google Colab Notebook and see how we can set it up. So first of all here, I'm just going to connect my runtime to a GPU. So you can change it here depending on if you have the Pro version in Colab, but this will also work on your own local environment. You can see the install instructions inside the GitHub repo. But when we're using Google Colab, the only thing that we need to pip install is RetinaNet. So this is what we're going to use for our face post estimation. It's basically going to extract the eyes, ears, nose, or whatever. You can also use like a pose estimation model from Ultralytics. You can go in and draw the bounding box around those poses, features that you extract from the head, and that's pretty much it. So it's just run here, it will connect to the runtime, and then we pip install our Retina face. After we've done that, we can start to just import all the different modules and so on. So let's just start writing all of those out. So torch, PyTorch, we need CV2 for OpenCV. Now it's actually going to predict it, so let's just get some help from AI. From RetinaNet, Retina face for the face detection. We also want from PIL, we want to import some stuff for our image. So image OS, we might need that later on. We have our image, and we also want to draw an image. There we go. And we have from TQDM, import TQDM for some tracking, or basically just for seeing how long our model takes to run the results. So this should be pretty much everything, or else we can just go in and import it later on as well. Let me just make sure that everything is installed. After that, we can go in and start writing out the code. There we go. Now we're good to go. We can set up a class to start with. Let's just call it Video Gaze Analyzer. So I have another video where we actually just go over for a single image, but now we're going to combine it into a class so you can use it directly. You just feed in a video, it's going to extract all the frames, throw it through the model, and then it will give an output video that you can then use, show whatever. You can use all the results in the different stages, through the face estimation, the heat map, the vectors, and what direction people are looking, and so on. This is very helpful in a lot of applications. So there we go. Let's now go down and define our init method. There we go. We have our video path. We have our output folder. We might need that. So let's just define it. We have our video path. So for the initializer, we don't want to have it here. So for that, let's just go and use CUDA. We'll just have that as a functionality later on for a class. So when we define our class, we'll just have our method with our input directory. For our video device CUDA, should be good enough. We can just print what device it's using. So when you run it in Google Colab Notebook, it's going to use GPU if you have set the runtime to that. There we go. Now we can go down and set up our model. So self.model. And we also need to get our transform. So transform. There we go, and we can use torch. So we'll use PyTorch to load our model. So that will be torch dot hub.load. We see it comes up with a suggestion here. That's not what we're going to use. We have the GitHub repo up here at the top. I can just read it. So it's like from FK Ryan / Gazelle. There we go. And we need to specify our model. That is the Gazelle using grounding Dino v2. And we have our other model, which is the VIT for our decoder. So that will be the large model 14, then underscore in out. There we go. So this is pretty much everything. We can set our model to the device, and we also put it in evaluation mode because we don't want to train or so on. We just want to run inference. Now we just set up some colors. Let's just set up some random colors. Let's say, what should we set? So let's just set up some colors. There we go. Let's just go for yellow, cyan. These colors are just for visualizing. Once we have like multiple faces in our image and so on, we want to visualize each color for each of them so we can see what direction they're looking. So we also have a color called lime. And we need tomato. I think that should be it. If we have more people, we can just always go in and apply more colors later on. Now we need to set up a function that can go in and process our frames. So let's just call it process frame. And this one will take a single frame. So this is basically just functionality that we have from the other video that goes in and does all the processing. We can just combine that multiple frames, take our OpenCV, open up a video capture with our video file, just loop through all the images, throw it through a process frame method here, and it will generate a video with the results. So right now, first of all, we need to convert our images. So we have frame RGB. And we set that equal to CV2. Color from BGR to RGB. So we have our image from OpenCV. We want to generate a PLL image. So we'll just call it frame PLL. Convert it from a NumPy array into a PLL image. Then we can take the width of our image and our height. Frame PLL size. There we go. And we can detect our faces on our frame PLL. So let me just copy paste this one, that one. We get our faces here. That's pretty much it. If we don't detect any faces, it's pretty much just going to give an error here, so we can go in and check. So we get our faces back here, or this will just be our results, because we're both going to detect faces, the key point in the faces, and so on. So let's now go down and extract the bounding boxes. There we go, bounding boxes. And let's go in and create a list. So we have our results. And from our results, we're going to generate like a key. So from our results, we're just going to loop through all the keys and extract the boxes. So I think this one here should be good. Let's just test it in a second. So we have our results. We have our key. Oh, this AI suggestion is not good. So our results. We will have our key. We want the facial area, so now it should be correct. There we go, for key in results, but results we should extract all the keys from our results, not just all of them, because we'll also have our values. So we both have our keys and values, and this should be pretty much it. We'll get our bounding boxes. We can always correct for it if we get any errors. Oops, I delete that one. So now we have our bounding boxes. We can just go in and check if the length of the bounding boxes is nothing. We can just return the frame. That should be pretty good to do as well. And now we can go down and normalize the bounding boxes. We need to do that before we feed it into our Gazelle model. So that's just a requirement. So we have our normalized bounding boxes. And we're just going to normalize it with the width and the height. So I think we should probably be able to do it like this. Yeah, I think this should be pretty okay. Then we can have our input image tensor, transform. We have our PLL image. That's also good. Yeah, that should also be good. We have our unsqueeze, self-divide, put it on the GPU. Now we have our torch node-grad, so we also want to generate our input, not just the input tensor, but our whole input should consist of our faces, but also our original image. So our input data here will basically just be our images. So that will be our im tensor. And we also have our bounding boxes, which will be our normalized boxes. Don't need to convert it to PyTorch tensors here, so the AI model was wrong. Now we use torch node-grad, so that's also good because we don't want to calculate any gradients, we just want to run in inference. So we have self.model, and again, let's just call this output instead. So self.model, there we go, and inside our model, we just basically just throw in our input data. There we go, and that's pretty much it. Now we can just go in and extract all the results, go in and visualize it, and so on. So now we have our output. Let's go down and create a new function for just visualizing all the data. I had that from the previous video. I'm basically just going to copy paste it from that script. So let me just grab it over here. And I'll just copy paste it in. So this is just another function for visualizing everything. The output from the model here will be the heat map, so we can just go in and extract all the information from the heat map and take the center of the heat map and just do our directions with that, or errors with that information. Let me just get the right indentation here. There we go. Now we have our visualize all function. We take in the PLL image, we take the heat map, bounding boxes are our faces, in-out scores as well. So basically just we predict how confident can we actually see the gaze in our image, and we also have a threshold for that. So if we're confident in our gaze estimation, we're just going to visualize everything together. It will just take the RGB channels, have an alpha channel with our heat map, and just apply it on top of that. It will go in and take the direction, so all the direction, to just take the center of the heat map and then just draw an arrow from the human eye to the actual direction he is looking, or the specific point where the person is looking. So this is pretty much everything that we need. Then we can just go up again. So now we have our visualize all. Go up here, we take the output, we just need to throw it through. We have our PLL image, we have our heat map, bounding boxes, in-out score. So this is pretty much everything that we need for calling this function. We'll just call result image. And our result image will be equal to, that will be our visualize all. So we have self.visualize all underscore all. And here we need to throw in our PLL image. So that will be our PLL image, frame PLL. There we go. And we have our heat maps. And our heat maps here will pretty much just be our output. So we can go and extract that first of all. So heat maps. So our heat map will be equal to our output. We can just extract the key from that. So we have our output and we have heat map. There we go. And we need to take the first element of that because it's going to be a list. There we go. This is our heat map. We need to get our bounding boxes. So that will be our normalized bounding boxes. So let's just call it boxes. And that will be equal to our output. Or we actually have our bounding boxes up there, so we can just take our normalized bounding boxes. Zero, there we go. And we have our last one, which is our in-out scores. They'll be equal to our output, in-out. There we go. And now we can just feed it in all the information. So we had heat map. We have our boxes. And we have our in-out scores. There we go. This is pretty much everything that we need. We also have a threshold, but we're just going to go with the default one. We'll get our result image. Once we have that, we can just convert it back to NumPy, so we can just visualize it with OpenCV, draw out a new video. So I have a video writer, write out our video frames with that one. So we have our NumPy result, which will be equal to our np.array, and that will just be our result image. There we go. And we also need to convert it, so np underscore result equal to cv2 cvt color. Have the np result here, and the color that we want to convert it to is color underscore RGB to BGR, not Bayer. And that's it. Now we can just return it, np underscore result, and that should pretty much be it. Now we can go down and create a last function, which is just a method for loading in our video stream. So now we can just call that process video. So we have define process video, input path. We will have our output path as well. And here at the end, we can have like a start time or duration or whatever. If you don't want to process the whole video, could be that we just want a specific region, specific timestamp. So let's just set that to 0, because we pretty much all the time just want to process all of it. Duration, set that equal to none. There we go. Now we have our function. Now we can open the file. So we have a capture with OpenCV. We're all familiar with this one here. So that should be pretty much straightforward. We get the frames per second. We can also get the frame width. There we go. That will be the integer of our cap.get. And then inside here, need to set our cv2 dot cap prop and then frame width, like that. We have $A here, should be like this. We can set the frame width, and we can also do the frame height and the total frames. So total frames, and we have our frame height here. There we go. Now we should have everything. We can just go down and start and calculate the end frames. So our start frame will be equal to the int of our start time. So that will be our input argument to our function. So our start time. And then we're going to multiply that with the frames per second that we have in our video. That's pretty much it. So if we have a duration as well, I'm going to calculate the end frame. And we set that equal to start frame plus the int of duration multiplied with our frames per second. So that should pretty much be it. Or else, you're just going to set the end frame equal to our total number of frames that we have in our video. There we go. We should have everything now. Now we can just go down and just set up our video writer, so we can output that to a new video, which will be an output video. There we go. We have to set up our 4cc. So the encoder, the format that we want to use, cv2.video writer underscore 4cc, I think it's like this. And we're just going to go with mp4. Now we can set up our output video writer. So that will be cv2.video writer. And that will be our output path. We set our 4cc, we set our frames per second, and we'll need to set the frame width. So the width should be the first one, and then frame height as the second one. If you get any errors, probably because like if it's not outputting anything to the video file, it might be because some of these stuff is off. If the frames per second is off, like it will just be slower. The width here need to be the exact same, or basically like what the output is that you're outputting to your video. So there we go. Now we have everything here. And now we can go down and just start the frame. So if you had another start frame, that one here, you just need to start the video at that point. So cap.set cv2.cap_prop, and we have pos, and then we have frames. There we go. Oops. Like this, and we're just going to set it to the start frame like that, and then we're going to use TQDM. So we have a track bar of how long it is. So the total is equal to our end frame subtracted with our, that will be subtracted with our start frame. And that will be a progress bar, P bar, and then we can set our frame underscore count equal to our start frame. And then we have the final one while cap is opened and frame count. And frame count is less than end frame. We have our return. So if it's successful, it's going to return true. And we have our frame, set that equal to our cap.read. Read in a frame from our video file. Could also be a webcam, so this is also going to work on a webcam. Could probably try to run that through in another video, but it needs to run on your own local system where you have access to the webcam. So if not read, if it doesn't return true, we're just going to break, because then we're not able to load in frame from our webcam or our video stream. And then we can have our processed frame that will be equal to our self.processFrame like that, and we're just going to throw in the frame that we read in from our video file. There we go. And now we can just directly write that to our video writer for output file. That's from OpenCV, so that we can just call it write. And we just need to throw in our processed frame. Just going to copy it like that, and we have our frame count. Plus equal 1. We have P bar update, and we update it with 1. And that's pretty much it. Then we can just go down and delete, clean up our code files and all of that. So after done processing all that, like we can just skip that for now. So now we have everything. Let's try to see if it actually runs. Right now we're not going to call it, so it will definitely run. There we go. We're going to go down and set up all the different stuff. So let's create our analyzer. Analyzer. And we set that equal to our video case analyzer. No input arguments. Let's try to see if it runs or we get any errors. Running CUDA, downloading the model, setting the model up, no errors yet. Downloading the model is not going to throw any image through yet, so we might not get any problems before we throw in some videos. We can set up the input path while it's downloading the model. So we have input path. And right now I'm just going to upload a random video. So just have a video laying around here. There we go. We can just upload it. Just going to throw in this video. If you look around, we got an error here. Let's just set up the input path to start with. So that will just be content, and let's just call it video.mp4. You can rename it. Video.mp4 and output video or output path, that will be equal to output.mp4. Okay, let's go up and check this one here. So let's see, got an unexpected keyword argument pre-trained. In our load method. So model entry, we try to load it from the hub. FK Ryan should be good. Gazelle should also be good. So we have our Gazelle Dyno V2. And pre-trained, I think this AI model here set it equal to pre-trained. Shouldn't have that, as it's saying in output and the outputs. There we go. We're just doing some live debugging as well, or recording the debugging. This is also very good to see. Because every time we run it, doesn't work the first time. If you see that, probably like they're just clipping. So now it's downloading the model from the hub. That's also one of the downsides. I don't really like the AI here inside the Google Colab. It doesn't really do a good job compared to other editors as Cursor, for example. So right now we have this. Run it. Shouldn't give any problems here. It's just path that we're trying to set, and now we can actually like call our methods. So we call our analyzer. Analyzer.process video. Oh, need to have a process video. We created that, right? Process video. Oh, it's all indented. Let me just try to see. It should be good now. Total frames. Gets that here. Misspelled it. There we go. Maybe we can fix some indentations here. Like that. Let's rerun it. No problems. We have our analyze process video. And here we just need to throw in our input video. Our input path. And we have our output path. We have start time. We also have the duration, but we're not going to throw that in now. We just want to process the whole video. Now let's try to run it to see if we get some results. So we can see 633 frames. It's going to process that. So right now we can see that it's just running it through the model with the retina phase. And now let's just wait until it has processed the whole video. We can take a look at the results after. It's just going to generate it into this output.mp4 file. Just takes a single image. Right now we're just processing one face, but we could go in and do multiple faces. If you go inside our functions up here, instead of taking the served element, the normalized bounding box is taking the served element of that. You can just have a loop running through it. So you can just have a for loop here. You can just ask AI to go in and do it, but you can just have a for loop running through all of these heat maps, all of the normalized bounding boxes, and go in and draw it on each individual person. So right now, let's try to see if it has processed the frame. Not yet, so it will probably take some time to run through it all. Again, this is running on a GPU. We need to do the face detection, throw it through the other model for the gaze estimation. We get the heat maps, then we need to extract the information, draw basically just from the human eye of the guy looking into the middle of the heat map, and then by using that we can see what direction the person is looking. So just wait until it has processed the video, and let's get back and take a look at the results. So now the video is done being generated. You can just go over to the left, you can right click, and then you can hit download on the output.mp4. Again, you can just take an arbitrary video, throw it into the system here. The notebook will be down in the description. You can just take it directly, throw it in there, it will generate the output video, and this is the results that you're getting. You can extract the intermediate, the results, all the elements from the pipeline. You can extract the faces if you want to use that in your own application and project. You can also, like for example here, we get a very good extraction where this guy is actually like looking, depending, even though it's really blurred out in the background, but also some pretty cool stuff here. Just have from the center of the bounding box to where we have the middle of our heat map. So this is very useful information, and you can take a look at the results. They are very awesome. This can be used for tons of applications and projects, and it's a very hard problem to solve. Now we just have a single model. You can just feed an image through it and it will do the job for you. So just take a look at the whole video. I'm just gonna play it and then we can take a look at it after. So if we actually like lose detections, it is because our threshold value, because we want to be able to make sure So if you get any error, so if you get any mispredictions or no predictions, as in this example here with the woman, it's because we have the threshold value. If we don't see the gaze, we're not going to make the predictions. Again, we can apply smoothing, filtering, and so on top of it. We can also make sure, go in and check so the bounding boxes doesn't flip or jump too much. So here we can see it jump from this face in the background to the foreground, maybe because it's blurred out and so on. So it's also based on the features, what we're feeding in from the feature extractor. We have the VIT backbone and all that doing the decoding. It's very good here for the guy with the green bounding box. He looks at the girl, the women, and then he looks down at the PC, and pretty much instantly you can see here it swaps from the women down to the PC. They're then looking at the computer, even pointing with the fingers, not taking any of that into account, but it looks very accurate where they act like looking. So even with where they're pointing with the fingers, the AI model act like thinks that it is in that area. It's not using the fingers, it's only using the faces, feeding that through the model, and we can see the guy in the background looking at the coffee cup and how it changes over time. So he's basically just taking a sip of his coffee, so it makes sense. He starts looking down the coffee cup here, he's preparing to lift it up. You can see how blurred the images are, so this is very awesome results. He's looking down the coffee cup, takes it up, gets it closer and closer to his mouth, and you can see his eyes is basically just following the cup. I think here at the end he actually like looks up to the person across him, but again, this is still a very good model. Very blurred out. Now we can see the crazy results when they're just talking to each other. Test it out on your video streams. You can just grab an arbitrary video stream, test it out on yourself, test it out on news media, podcasts, and so on. There's pretty much endless possibilities. Very awesome. You can also use it like if you have self-driving cars, if you want to monitor if people are looking out the windshield, if they're looking at their phone, down, whatever. So instead of doing like post estimation, face estimation, trying to do all sorts of stuff, I also have videos covering that in previous videos, like probably 2-3 years ago. Now we have AI models that can do a lot of this work for us. So definitely go and check it out. Again, everything will be down in the description. Hope you guys have learned a ton from this video here. It's a more detailed one. We went through it step by step in the code so you guys can see how to set up a whole pipeline. We just have a class, we can call a single method, we get the results, and that's it. Hope to see you guys in one of the upcoming videos. Until then, happy learning.